Okay, now we're going to move on to chapter chapter 30, which you guys know is the last chapter we're going to cover anything from. And there's just a couple things I want you to get out of chapter 30. Now, you'll recall that beginning of the course, it all started with the discovery that two charges, well, the discovery of charge, but then the idea that you could understand the interaction of these charges with the outside world by realizing that they exerted a force on one another. And that was just Coulomb's law. But then everything after that for quite some time was just various permutations of that. We were just looking at the implications of this, and we were also defining a bunch of new things that would make our lives more convenient in some other context. So, for example, we defined resistance, we defined potential difference, we defined capacitance. We defined all those things and more, some of which I'm not mentioning at the moment. They just came from Coulomb's law, but it was much more convenient rather than trying to calculate Coulomb's law for every single situation. It's a lot more convenient to use these other things that we define along the way. And that's really the only reason there. There's not really any new physics in there. There's just new definitions. Well, that's pretty much what's happening now. We started with the idea that we had a Lorentz force, which is a QV cross B, which is that strange magnetic field force, and then we defined some other things based on that. So, for example, we defined that a magnetic flux that you could get from this field that exerts a force on moving charges. We then Lenz's law, which we just talked about. That's another thing which we just defined. Okay, so I think I will leave it with that, except to say that what we're about to do is exactly that. We're going to continue that on just a little bit more. So now let's look at this situation. Let's look at the situation where we have a solenoid of a certain number of turns. Okay. So let's say it's got an area A. I'm not going to worry about the R. We'll just call it an area A. It's got a length L. And it's got N turns here. Let's see, do we need any other information? No. So what we want to know is if this is put out in a region where there is a magnetic field, and just to keep things simple, it doesn't make it a difference conceptually, but it will make our lives much easier in terms of our calculations if we just always make it so this B is aligned with the axis of this. So basically our B dot dA will always be BA cosine theta equal to 1. So it's just going to be B times A. Okay, so what we want to know is how much magnetic flux is going through here. Well, we just said it. That's just B times A. But what we really want to know is what's the change of this magnetic flux with time. And of course, you guys know now why we want to do that, because if we take the negative of that, we get the potential difference that is created. We get the electromotive force created by this change in flux. However, there's one more thing for this coil. This is what happens with one coil. What happens to the coil underneath it and the coil underneath it? They all get the exact same EMF. So what do we really have here? I'm just going to go ahead and put it here. I'm just going to squeeze it in there. That our total EMF is going to be equal to this. All right. So let's see. Yeah, let's leave it at that for the moment. Okay. So now here's the question. What happens if we run a current through this coil? If we run a current through that coil, it creates a magnetic field. If it creates a magnetic field, that magnetic field has a flux through this area. And if that magnetic field is changing, i.e. if the current is changing, then this will generate an EMF. It will generate an electromotive force. so what is the magnetic field created by a solenoid? I don't think we actually derived this in class. I'm hoping you guys took a look at the section in the book, but I believe, let's see if I can get it right. I believe we just have mu 0 n I over L. And so that's the magnetic field created by a current going through a solenoid. Okay, so that's all I'm going to do now is plug that into this expression right here. So what do I have? I have minus n. I'm pulling that outside. The a, I'm also going to pull that out here, out of the derivative. I'm also going to take everything else here that's not a function of time. So mu 0 is not a function of time, n is not a function of time, and L is not a function of time. So what's the only thing left that's a function of time? It is the I dt. And this is now equal to the EMF. This is just another expression for things. So I'm going to do two things at once here. What I'm going to do is I'm going to introduce our new definition. Our new definition is we are going to say that the EMF is defined as, I'll say this other, that there's a new property which is defined as the ratio between the EMF and the time derivative of the current. So what does that mean? It means that we have some new number that we're going to call L that, I'm going to put a minus sign there just because that's how it's defined. So we are going to define this new thing L, and this new thing L is called the inductance or the self-inductance. There is a section in your book about mutual inductance. We aren't going to worry about it a whole lot. It's probably a good idea that you read through it, but it's, like I said, we aren't going to worry about it a whole lot. Okay, I'm just going to move a couple things around here. Okay, so, all right, let's see. So I want to keep a couple of these things. There, I guess that will motivate me to change colors. So what do I want to keep? So, first of all, let's make a note of this. L, for a solenoid, we now know just by looking at these two equations here, we can figure out that L is equal to mu 0 n squared A over L. Did I forget anything? Nope, that's it. So mu 0 n squared A over L. All right. So this is the inductance of a coil. A coil of area A, length L, and number of turns N. Coil, solenoid, I use those two terms interchangeably. Your book uses them slightly differently, but it doesn't matter. Okay, so we're going to write that down here. And also, just to remember this, we're going to pop this up here too. B equals mu 0 n I over L. Okay, and just draw your attention, I'm going to draw your attention once more to this because I'm about to erase it, but I'm going to rewrite it in a slightly different form. And, excuse me, I'm going to try to get that color back. Okay. All right, we got this. All right, and we have it. All right, so now what I want to do is I want to calculate what's the power that goes into this, into a solenoid. Well, what's the power? We are going to use Pi's law, P equals I E, where E is EMF. But we now know what EMF is. It is, I'm going to go ahead and write it like this. I'm going to put the minus sign out here for now. I, L, di dt. Okay, so all I did was use the expression for EMF that I just erased, which is minus L di dt, and I put that into this expression, and now I got Pi's law. Now what we're going to do, this is the power that is the power of the solenoid the question that I'd like to ask is, how much energy does it take to get a solenoid charged up? Well, what is power? Power is just energy per unit time. Well, here's our unit time right here. So we're just going to take this P dt over here. What I'm also going to do, because now what I'm talking about now is the energy being supplied to this solenoid, I'm just going to, well, it's just the minus of this, right? This is the energy the solenoid, or excuse me, this is the power the solenoid dissipates. Where does it come from? And I'm using the word dissipate. It's not the right word. I guess I'm gonna give it away and say this is the power the solenoid stores. Okay, so. But what I'm looking at right now is what's the energy that needs to go into the solenoid to get it to store a certain amount of power. All right, so let's go ahead and, okay, so I was a little loose with the definitions there with power and energy, but you guys are sticking with me. It's all right. So what do I have here? I just have L-I-D-I. Well, if I want to get the total energy, what do I want to know? I want to know, it seems reasonable to assume that a solenoid that has no current in it, that has no energy, right? There's no moving charge, nothing is happening, it's just a chunk of metal sitting on the table. So what gives it its energy? When we get current. So if we start from zero current and we go up to some I, what we will be doing is going from some zero energy to some energy U. And so I'm just going to rewrite this as U equals, as a matter of fact, I'm just going to do this in one step here. L, and what's the integral of I di? It's just 1/2 I squared. And I'll go ahead and say, make it this I1, so we now recognize this is a specific value of current. So we started with no current. We went to a time when there was a current I1. As we did, we had to supply this much energy to this solenoid. Therefore, since we started with a solenoid with no energy, the energy contained within this solenoid is just this. 1/2 L-I-1 squared. Where I1, like I said, that's just some value, whatever value of current that you happen to be at. All right, now let's go ahead and look at this in slightly more, well, this is an important result, first of all, that the energy contained within a capacitor is equal to this. So remember that. As is, well, this is not the result, as these are as well. As a matter of fact, here we go. I'll just write it up here. U equals 1/2 L-I squared. Okay, I'm going to do one more thing now. Now, let's go ahead and see what this is, what this energy is in terms of this magnetic field. So if we solve this magnetic field, if we rearrange this equation to get I by itself, what we end up with is we have BI equals BL over mu 0 N. Did I get everything? L mu 0. Yes. Okay. So I'm going to put this back into this expression over here, and I'm also going to put this back into this expression. So U equals 1/2 mu 0 N squared A over L times I squared, which is B squared L squared over mu 0 squared N squared. So what happens? We have an N squared that cancels an N squared. We have a mu 0 that cancels one of those mu 0s. We have an L that cancels one of those L's, and I believe we're done. So, what do we have? This equals 1/2 B squared over mu 0 A L. Now, What is AL? Do you remember when we did the energy storage in a capacitor that we had the same kind of expression there? That is the volume of this solenoid. That's the volume of that tube. The contained within the wires is A times L. So what is then the energy density of a magnetic field? It's just this divided by its volume. So U per V, so energy density per volume, is just 1/2 B squared over mu 0. And in the same way that when we did that calculation, well, first of all, it'd be a good idea for you to look back at the expression for the energy stored in a capacitor and compare that to this one. But the second thing I'd like you to do is remember, or I guess you aren't remembering since I'm telling you, although we are calculating this for this solenoid, we're calculating this for this specific situation, this is not limited to that. This is just the energy density that is stored in a magnetic field. It doesn't matter where that magnetic field comes from. This is the energy density of a magnetic field. So any magnetic field anywhere will be containing this much energy. And that's that. We only have one more video to go.